Welcome back to the Packet Lab. Today we're going to take a look at another in our OSPF lessons, and today we're going to take a look at the OSPF network statement. The OSPF network statement is going to be used to assign interfaces to a particular OSPF area. And when you're running OSPF, all the interfaces that are active in the OSPF process have to be assigned to a particular area. There's actually two ways to accomplish this. In this lesson, we're going to take a look at the OSPF network area configuration command that's used in the routing process level. There's also an interface level command, which is IP OSPF network, which accomplishes the same task. I'm going to take a look at that in a different lesson. I would strongly suggest watching these lessons in order so that you can compare and contrast these two commands. The interface level command, the IP OSPF network command, is newer than this network area command, so I like to consider the network area command as a classic command, whereas the interface level command can be considered a nouveau or whatever, modern, I guess, version of that same command. They both accomplish the same task, they just go about it a little bit differently. The OSPF network area command is going to allow you to assign multiple interfaces to an OSPF area with a single command. That's both the strength and the tricky bit of the command. And the way it's going to do that is it's going to use a combination of a network and a network mask to define an IP address range like an access list. And like an access list, instead of using a network mask, it's actually going to use wildcard bits. And we'll get to that in a minute here. But if you've worked with access list, you'll be familiar with wildcard bits. If you haven't, they're a little bit different than network masks, and they might take a little bit of getting used to, but we'll run through that. So then any local interfaces that have an IP address within the range specified in the network area command is going to be assigned to the OSPF area that you define in that command. Like I said, that's a strength. You can have a single statement and assign every single interface to an area if you like, whereas the interface level version, as we'll see in a different lesson, you have to actually go under each interface and configure it. So even though it's the classic / old version, it does have some advantages over the newer interface level command. This information is directly out of the command reference guide, and you can see here that the command is network followed by the IP address. The IP address in this case is going to be your network IP address, the wildcard mask, and then the area, and then the area ID. So it says here the IP address and wildcard mask arguments together allow you to define one or multiple interfaces to be associated with a specific OSPF area using a single command. Basically, it's saying you're going to define a range of IP addresses and assign anything in that range to the area that you choose. Using the wildcard mask argument allows you to define one or multiple interfaces to blah, blah, blah. It's basically saying the same thing twice. It's kind of telling you that, the wildcard mask is going to be the powerful bit here. And I've got this bracketed by what the fuck, because I don't understand what they're talking about here. It says, if you intend to associate areas with IP subnets, you can specify a subnet address as the value of the area ID argument. The only thing I could think of here, and this is a little bit off topic, is that when you specify an area ID, you can specify it as a dotted quad, basically. Instead of doing area 1, you could do area 0.0.0.1. So you can actually have areas that match your IP subnet. So if you had an IP subnet of 10.1.0.0/16, you could have the area be 10.1.0.0. I think that's what they mean here. Otherwise, I have no clue what they're talking about. And really, I don't know anybody that really does that. Usually they just use integers for the area, but either way, that's not going to be important to this lesson. So moving on, this next bit is related to secondary addresses. I detest secondary addresses with a passion. If you don't know what a secondary address is, consider yourself blessed. It's really just I don't know. I don't want to use the language that is in my mind right now to describe secondary addresses. Basically, you can have an IP address, a primary IP address, and then a secondary address assigned to an interface. If you happen to have that goofy ass setup, what you got to keep in mind is that your network area command has to cover the primary IP address. If you haven't matched the secondary IP address and the primary IP address is not matched within that statement or another network area statement, OSPF will not be enabled on that interface. It has to match the primary. So hopefully that didn't mean a whole lot to you because you don't have secondary addresses, but if you do, just keep that in mind. So most of this is pretty straightforward. It's just defining an IP address range, and then any local interfaces that have an IP address that is within that range get assigned to the OSPF area that you specified. Easy peasy lemon squeezy, right? Well, that depends on whether or not you've worked with wildcard masks before. If you've created access lists, and I have lessons on access lists, and you've played with these guys, they're a little bit different than the network masks that you may be used to. So when you assign an IP address to an interface, you assign an IP address and then a network mask. When you're using the network area command, you're going to use a wildcard mask rather than a network mask. So basically, on the simplest level, you can just think of a wildcard mask as a subnet mask where the ones and zeros are inverted. So if you have a network mask of quad 255s, you would change all the ones, because quad 255s is a string of 32 ones. You would change it to a string of 32 zeros, which would end up as quad 0. And if you had a /24, it would end up with 3 zeros followed by the 255. So you can see here that anything that's a 255, you change to a 0. Anything that's a 0, you change to a 255. This is pretty easy to understand from a contiguous bit standpoint. What I'm talking about with contiguous bits is that here you've got contiguous ones. It's all ones. Here you've got 24 ones followed by 8 zeros, 16 ones followed by 16 zeros, 8 ones followed by 24 zeros, and here's all zeros. So you don't ever have a situation where you're going 1, 0, 1. So it's pretty easy to change these. When you get to the CCIE level, and maybe even the CCNP level, you're going to start playing with wildcard masks that don't have contiguous ones and zeros, and that's where the fun comes into play. Also the power of the wildcard mask, where it actually is a benefit over a network mask, but we're not going to get into that today. For real basic use of wildcard masks, just remember that if you know what the network mask is, just invert the zeros and ones, and it's pretty easy to do. So with a wildcard mask, once you've inverted, if you have to convert from a network mask to a wildcard mask, the most important thing to keep in mind, and this is on a binary level, again with the contiguous ones and zeros, it's not that big a deal. It'll be pretty easy to do in your head, as we'll show you. But on a binary level, a 0 in a wildcard mask means that I must match. A 1 means I don't care. It can be any value here. So if you have a network command of network 10.1.123.5 and then 0.0.0.255, what it's going to say is, okay, my first 3 octets are all zeros, so those must match. So when I'm looking at this address, I care about 10.1.123. This last octet, because it's all ones, which is 255, I don't care. This can be anything from 0 to 255 and it will match. So this is the range that you have here. So the range you have is going to be 10.1.123.0 through 10.1.123.255. So it's very similar to how a network mask. So if we were to do this with a network mask, we would just invert this, where we would say 10.1.123.5, and really we should be using a 0 here, but this is just for demonstration purposes. And then we'd use 255.255.255.0, which is a /24, which would match the same range. So if you know network masks, wildcard masks aren't that hard to get your head around. Unfortunately, I'm going to take you down the path of a little bit of binary math here, so stay tuned for the pain. Alright, as promised, we're going to dip into a little binary math, discrete math, if you will. So if you study logic or discrete math, you remember these tables. So a logical AND operation, what it's going to do is it's going to take either a 1 or a 0 in this case, or if you're doing logic, true or false. When you run an AND operation, you say 0 and 0, it's going to equal 0. 0 and 1 is going to equal 1. 1 and 0 is going to equal 0. And then 1 and 1 is going to equal 1. So basically the takeaway here is that anytime you AND two binary numbers, if there's a 0 involved, the answer is always going to be 0. If it's 2 ones, then you're going to end up with a 1. So anytime there's a 0, it'll end up with a 0. Otherwise, you'll end up with a 1. And that's an AND operation. And really, I don't know why I showed you the AND operation, because the guy that we're going to be using today is going to be OR. So an OR, simplify an OR operation. Anytime there's a 1 in the mix, your answer is going to be a 1. So 0 or 1, 1 or 0, 1 or 1 is always going to equal 1. The only time when you don't have a 1 for the answer is when you're ORing 2 zeros. So 0 or 0 is going to equal 0. So keep this in mind. I'll have this little table on the slides when we need to use it, but we're going to be using a logical OR operation when we're working with wildcard masks. So you're probably like, thanks for the refresher, but what the hell do I need to know this for? This is why. This is from the command reference. It says, Cisco iOS software sequentially evaluates the IP address wildcard mask pair for each interface as follows. It's going to take the wildcard mask argument, and it's going to logically OR it with that of the IP address. It's going to take the wildcard mask argument again. It's going to logically OR it with the IP address argument in the network command. The software compares the two resulting values. If they match, OSPF is enabled on the associated interface, and the interface is attached to the OSPF area specified. So to restate that probably more simply is what's going to happen is it's going to have an algorithm that's going to take the target IP address, OR it with the wildcard mask. It's going to take the network that you've specified and OR it with the wildcard mask. It's going to compare the results of step 1 and 2, and if they are the same, then you're golden. It's going to match that IP address range, and it's going to be assigned to the area that you have determined, and if not, then it's going to fail and it will not be assigned to that area, unless of course there's another statement that matches it. But assuming that there's only one statement, then that's what's going to happen. So let's use this statement of network 10.1.12.0, 0.0.0.255 and figure out which of the following IP addresses will match. And when I say following IP address, I'm talking about 10.1.12.123 or 10.1.123.1. Yuck. Binary math, huh? Didn't want to go down this path. And actually, you know what? The reason I'm doing this is just to give you the underlying algorithm and structure and how this actually works, how iOS evaluates these commands. Really, we can take a quick look at this, and if we remember that zeros are our must matches in our wildcard mask and the ones are don't care, we can see here that we would have to match on the first 3 octets, and our network is 10.1.12 in the first 3 octets. So really, we don't need to go through the binary to figure this one out. Again, this is more of a learning exercise. Where this will come in handy is if you know how this works when you get to the CCIE level or you start writing intricate access lists. This will come back because that's where the power of the wildcard mask is that you can use non-contiguous wildcard bit mask to do some pretty cool stuff. But this is just going to show you how this works on an iOS level. You can skip ahead if you don't want to go through the ones and zeros. So anyways, what we're going to do is we're going to do an OR operation on our first target IP address, which is a 10.1.12.123. We convert this into binary, write it out, and then we convert our wildcard mask of 0.0.0.255 to binary. So if you have to use a binary calculator to get this, fair enough. This one you shouldn't have to because it's all zeros followed by all ones in the final octet. Now we start doing our OR operation. Now remember, with our OR operation, it's going to always be 1 unless both operators are a 0. So basically we go in 0 or 0 is 0, 0 or 0 is 0, and we keep doing this. 1 or 0 is 1. Remember, if there's a 1 in the mix, it's going to be a 1. So basically this is going to be kind of trivial because if you've got all zeros, it's just going to carry down whatever the value is of the target IP address. So you can see here that we've carried down all these bits unchanged for the first 3 octets. Now when you get to the last octet, just the opposite. Anytime there's a 1 in the mix, it's going to always end up with a 1 for the answer. So we really don't have to do a whole bunch of math here. I mean, 0 or 1 is 1, 1 or 1. Basically anything in this octet is going to end up as a 1. So we end up with 10.1.12.255, and we're going to keep that value. Do the same thing with the second IP address, break it out into binary. We can just cut and paste our wildcard mask and do our operations, and we'll simplify this. Like I said, you can go through with each bit and do the operation here, but to simplify these first 3 octets, basically because it's zeros, we're just going to carry down everything that's in this target IP address. It's going to come down unchanged. So we end up with the 10.1.123, and then this last octet's going to be 255. So you can see how pretty easy to do this in your head, and breaking out into binary here isn't really necessary, but we're gonna go ahead and just show you this at the 1s and 0 level. So the final thing we're gonna do is we're gonna take the network address, which is 10.1.12.0, and do the same thing. We're gonna OR with the wildcard mask. Again, the first 3 octets are gonna come down unchanged, and this last octet's gonna be all 1s because we're ORing with 1s here. So we end up with 10.1.12.255. So now what we're going to do is we're going to take the results of step 1, and for our target IP address 1, it's 10.1.12.255. That matches the logical OR of our network IP address and the wildcard mask, which is step 2. So this guy is going to match. It's in the range. This second IP address does not match when we take a look at the results of step 1 and step 2. So it is not in the range. So that's how you do it on a binary level. Again, you probably won't do this a whole lot in the real world until you get to non-contiguous wildcard masks, because it's pretty easy to do this with just going, okay, I care about the zeros, I don't care about the 1s. So basically I know that when I see a wildcard mask of 0.0.0.255, first 3 octets have to match this network address. That last octet can be anything. So we can see here that this third octet doesn't match, so we don't have to worry about this. We can see that the first 3 octets match match on target IP address 1. And since we don't care what the last octet is, it can be anything from 0 to 255, it's going to match. So you're probably like, wow, thanks for the access list review. That's great. That's not the command that we're learning today. Basically, the network area command is going to be an access list. What it's going to do is it's going to say, I have a range of IP addresses that I'm going to evaluate each of my locally assigned interfaces. And if they match that IP address range, I'm going to assign them to this OSPF area. So here we can see this in action. We get on there and we get into the router process, the router OSPF1, and we issue the network 10.1.12.0 with the wildcard bits of 0.0.0.255, and we're going to assign anything that matches that range to area 1. So if you see these IP addresses here, you may remember them from the last few slides when we were doing the binary math. 10.1.12.123 is going to match this range. 10.1.123.12 is not going to match this range. So interface 00/0 is going to be assigned to area 1. And interface 00/1 is not going to be assigned to an OSPF area, so it's not going to be running OSPF on that interface. So the big takeaway of this is that the network area command is going to be a range of IP addresses. So it doesn't have to match exactly the IP address of, let's say in this case, 00/0. You don't have to have 10.1.12.123. As long as this address is within that range, it's going to be assigned to that area. In this case, 00/1, since it's not in that range, it's not going to be assigned to area 1, since this is the only statement, which is kind of letting you know in the future that you can do multiple statements with multiple different areas. It's not going to be assigned to an OSPF area, therefore it's not going to be running OSPF unless the interface level IP OSPF network command is configured, but that's for the next lesson. So here we see the advantage of the network area command in that you can have a single command that's going to match multiple interfaces. In this case, we're looking at network 10.1.0.0 with a wildcard bit mask of 0.0.255.255. And what that's saying is that anything that starts with 10.1, let's go ahead and assign that to area 1. So we have two interfaces here, 00/0 and 0/1, and they both start with 10.1 in their first two octets. So they're both going to match this network area command range. So consequently, both of these interfaces will be assigned to area 1. So you're conserving configuration here. You're saying here's a range, assign all the interfaces that match, so you can have anywhere from 1 to every single interface on your device match this statement. Keep in mind that the network mask of the interface does not have to match the wildcard bits in the network area statement. So here we have a network area statement. We're saying let's match everything within the 10.1.12.0 basically /24 range. We're saying we care about the first 3 octets. We don't care what value is in that last octet and assign that to area 1. This is a /24. Under the interface, we can see that we have this set up as a /28, whereas our network mask is 255.255.255.240. In wildcard bits, that would be 0.0.0, and then you invert this last bit, it's going to be a .15. Doesn't matter. These don't have to match exactly. As long as this IP address falls within the range of this network statement, it's going to be assigned to that area. So here we see the advantage of the network area command in that you can have a single command that's going to match multiple interfaces. In this case, we're looking at network 10.1.0.0 with a wildcard bit mask of 0.0.255.255. And what that's saying is that anything that starts with 10.1, let's go ahead and assign that to area 1. So we have two interfaces here, 00/0 and 0/1, and they both start with 10.1 in their first two octets. So they're both going to match this network area command range. So consequently, both of these interfaces will be assigned to area 1. So you're conserving configuration here. You're saying here's a range, assign all the interfaces that match, so you can have anywhere from 1 to every single interface on your device match this statement. Keep in mind that the network mask of the interface does not have to match the wildcard bits in the network area statement. So here we have a network area statement. We're saying let's match everything within the 10.1.12.0 basically /24 range. We're saying we care about the first 3 octets. We don't care what value is in that last octet and assign that to area 1. This is a /24. Under the interface, we can see that we have this set up as a /28, whereas our network mask is 255.255.255.240. In wildcard bits, that would be 0.0.0, and then you invert this last bit, it's going to be a .15. Doesn't matter. These don't have to match exactly. As long as this IP address falls within the range of this network statement, it's going to be assigned to that area. There's 2 very important wildcard masks to be aware of when you're working with a network area statement. The first one is a quad 0. So all the bits are set to 0. And with wildcard bits, anything that's a 0 is a must match bit. So basically this is saying that you have to match all of the bits that are specified in the network portion. So it's going to be, let's see here, it's actually easier to show you an example here. Network 10.1.12.1 quad zeros area 1. What this is saying, all 4 of these octets are important, all these bits are important, so it's going to match only on that IP address 10.1.12.1 and assign it to area 1. It won't match any other IP addresses. So this is analogous to a host route. The second is the quad 255s, and as you can figure out, these are the don't care bits, which means that, well, when it's I said well because there's going to be another slide that tells you why this shouldn't necessarily be true, but when combined with the network address of quad zeros, it's going to match all interfaces, no matter what it is, all IPv4 interfaces on your device. And this is kind of analogous to a default route. So here we're saying any network here. So any quad zeros matched with the quad 255s for your wildcard address, it's going to match every single IPv4 interface, and it's going to assign it to area 2. You might be thinking, oh, okay, cool, that sounds great. What happens though when you have multiple statements? This 10.1.12.1 address, it obviously matches this quote unquote host route, if you want to use that analogy, but it also matches this quote unquote, again using the analogy, default route. So is this guy in area 1 or area 2? It's a good question. We're going to table that for a different slide coming up real quickly here. But the other thing that comes into play here is this quad zeros. Why you have to use quad zeros, because, well, I'll show you in the next slide. All right, this is a little bit off topic, but since we did do the binary math early on, it's actually kind of relevant because really, technically, you should be able to use any network address combined with the quad 255's wildcard mask, and that should match for all interfaces. But OSPF requires that you use the quad zeros. So let's take a look at the binary real quick. Here's our OR table up here, that anytime you have a 1 on either side of the OR operation, the result is always going to be 1. So whenever you OR anything, these X's could be any, it could be either 0 or 1, so any IPv4 address that you can think of, you OR it with the quad 255s, the result will always be quad 255s. Okay, so any target ORed with that wildcard mask will be 255s. Big flippin' deal. Okay, so any network IP ORed with that wildcard mask will give you the same thing, because again, one side is all 1, so it doesn't matter what you throw on this side, 1 or 0, it's always going to end up as 1. So again, you're going to end up with quad 255s. Well, if you remember our algorithm, you OR the target IP address with the wildcard mask, and then you OR the network IP address with the wildcard mask, and then you compare the results. If the results are the same, then the address matches. So any possible IPv4 address and any possible IPv4 network address with the quad 255s for your wildcard mask is going to result in quad 255s. So you could use any value for the IP address, so every IP address would match. And more importantly, you should be able to use any value for the network mask. So why do you need to use the quad zeros in iOS? Well, the reason you have to do that is because of a little feature with iOS. It has been implemented to assist you in the conversion of network masks into wildcard bits, and we'll see that in the next slide. So iOS is actually going to take a look at your network area command, and what it's going to do, it's going to say, okay, you're going to give me the network IP address, and then I'm going to take a look at that next argument. That next argument should be your wildcard mask. Well, let's take a look at this first line here. It's going to say, okay, you gave me the network, and then you gave me a wildcard mask of 255.255.255.0. So it's saying, oh, you know what? Wildcard mask shouldn't start with a 1. There shouldn't be a 1 that begins the wildcard mask. What this guy's obviously done is he's just got under the interface and taken the network mask and popped it in here. Well, since I'm iOS and I want to be helpful, what I'm going to do is I'm going to go ahead and convert that network mask into a wildcard mask. So it just does the little binary stuff of inverting the 1s and 0s, and you can see down here it ends up with 10.100.1.0, 0.0.0.255 and assign it to area 1. So you can see the argument that we provided for the wildcard mask is changed from what iOS presumes to be a network mask to a wildcard mask, which is kind of cool. The other thing you might notice here is that it's going to go ahead and just put a 0 in for any don't care bits in the network mask too. So while we put in 10.100.1.1, it only uses 10.100.1.0 because it's saying, I only care about the first 3 octets. This 255 means I don't care about the last octet. So that's actually kind of nifty. And you can see here that it does the same thing for these 2 network area statements, which are a little bit more tricky because we're not using, full octets here. Basically, this is going to be a /20 address where we've assigned 1s to the first 4 bits of the 3rd octet. So it's going to convert that from 255.240.0 into 0.0.15.255. Sweet. It's also going to take this network and it's going to convert that to a network with using the bits that we care about. So we care about the first 2 octets, so we keep the 1.1, and then the third octet, without getting into network mask too much, we leave this as a 0 in this case. And you can see here the next one, even though we specify 164, it's going to use 160 as the network address. I'm not going to go too deep in this because that's going to dive into IP addresses and subnet masks and all that stuff, but it does this conversion for you. Pretty sweet, huh? Well, it is a sweet feature for the most part, but this is the reason why you have to use the quad 0 network with the quad 255 wildcard mask if you want to match on all interfaces. Because you can see here we put in network 1.2.3.4 and then all 255s for our wildcard mask and assign it to area 1234. Using the logical operation, what this means is that I want every possible IP OSPF interface on my device to be assigned to area 1234. Unfortunately, when iOS gets a hold of this, it's going to say, oh, you started your wildcard mask with a 1 because the 255s are all 1. So it's the first bit it's going to see as a 1. It's like, oh, that must actually be a network mask that you pasted in there. And I'm going to convert it to quad 0s. And it leaves your network unchanged because it's saying, well, since this is quad 0s, that means that every single octet is important. I'm going to leave it the same. So what you put in thinking would match every single interface on your device actually ends up matching only 1. It ends up with the analogy of the host route. It's saying match only this IP address and assign it to area 1234. Completely different than what you may have thought you were typing in there. So the important takeaway here is that if you want to match everything, you have to use a network of quad 0s. So here it's going to say network quad 0s, wildcard mask, quad 255s, all interfaces on this device be assigned to area 1234. And that's exactly what it's going to do. iOS is going to say, oh, your wildcard mask starts with a 1. You must have actually inputted a network mask instead of the wildcard mask. Let me convert this for you. But then it's going to say, well, wait a second. You did put in quad 0s here, so you meant what you typed here. So I'm not going to invert the bits here, thinking that you had actually entered in a network mask instead of a wildcard mask. I'm going to leave the statement exactly the way it is, and then you end up with what you want to hear, where it's saying any possible IPv4 address on this device needs to be assigned to area 1234. Probably a long way around, more information than you needed. The takeaway is just remember that if you want to match all possible interfaces, use the quad 0s and the quad 255s and then assign it to an appropriate area. Okay, so this is going to be our topology such that it is. The topology is going to consist of a single device, R1, and rather than have actual connections, we're going to use loopbacks and just assign them different IP address ranges. So we got loopback 0 and then loopbacks 10 through 15 with various IP addresses and subnet masks. Okay, so remember a few slides back I told you to table that where we had the case where we have an IP interface that matched 2 different network area statements. So in that case, which area does it get assigned to? Because you can't have an interface be assigned to 2 different OSPF areas. It has to be a discrete area. It has to be a single area. So the answer to this is that it's going to be assigned to the most specific match. And the way it does that, well, let me start with this. In older versions of iOS, and I'm thinking it's 12.2 and older, I'm not sure, I didn't get the actual iOS version. If you're running 12.2 or older code, you need to upgrade your code. So hopefully you never run across this in production, but never say never. You see some weird stuff out there. What would happen in those older versions, it's going to assign the areas based on the first statement that matches. So as you input your network area statements, it's going to put those into the configuration in the order that you've inputted them. So in this case, we've got router OSPF 1, and our first statement is network quad 0s, quad 255s, and then we're assigning all those to area 0. So if you're paying attention, you know that this is basically the catch-all. So any possible IP address, IPv4, I guess I have to be specific, on this device is going to be assigned to area 0. And it's just like an access list. Once it matches, it never goes on to evaluate these other network area statements. Now this is the old version. This is the version 12.2 and older. Again, I keep saying 12.2. I'm not sure on that. Old school, that's what it did. So the order of your network area statements was very, very important because it would evaluate these in order. So in this case, it's never going to evaluate any of these other network area statements. So the nice thing is that the newer versions will actually take your network areas. iOS will go ahead and reorder them in the configuration. So let's see that on the next slide here. So modern iOS versions are going to take your network area statements and they're going to reorder them so that when they appear in the running configuration, the most specific statements are going to be listed first. So here's our input. We go into the router process and we put in 5 different network statements. Now with the old version, it would show up in the running configuration in this exact order. As we saw in the last slide, we would never get past the first statement because everything would match that. But if we do a show run and we're just doing a section router OSPF to just get to that section, we can see here that these don't show up in the order that we entered them. So this area 0 is actually at the bottom. And the reason that is because it's the least specific. It's basically the catch-all. It's saying that, everything matches this. Whereas this first command is a quote-unquote host route, so it's only going to match on 10.1.1.1, and it's going to assign it to area 4. So that's pretty cool. So I don't know if the algorithm that iOS uses is that it searches through every single network area statement and then matches on the most specific one, or it's still using that algorithm of I'm just going to take these in order, but because iOS now reorders these automatically for you, you're essentially going to match on the most specific because they're in the order of most specific to least specific. So it doesn't really matter. The end result is the same. I don't know what the specific algorithm is, but it might be good to look it up just to amaze your friends at networking cocktail parties. So we can see here these been put in descending order from most specific. So the most specific is this quote unquote host route, and then the /16 and the /8, and then of course the match everything. Now you might notice here that we put in 5 network area statements and we came out with 4 network area statements. This is pretty important because what we did here was we put in this statement, blah, blah, blah. We'll notice here that there's no statement for area 1. So when we put in area 1 statement, we put network 10.0.0.0, and then wildcard mask is 0, 255, 255, 255, and we assign that to area 1. Basically, that's saying that anything that's a 10.0.0.0/8 assigned to area 1. So really anything that starts with 10 in the first octet gets assigned to area 1. Well, where the hell is this? Let's go take a look. So this is our area 2. That guy's in there. Here's our area 3. That guy's in there. Well, look at area 3. So we put this in after we had put in our area 1 statement. Well, we have a network of 10.1.1.0. Oh, that's a different network. 0.255.255.255. This is not a different network. So really it's saying here that because the wildcard mask is zeros, I only care about that first octet, so I only care about this 10. I don't care about the rest of this. So when this goes into your configuration, it's going to be 10.0.0.0 with the 0.255.255.255 area 3. And we see that guy down here. So this is exactly the same as this as far as iOS is concerned. So this is important to keep in mind that you have to keep an eye on your network address. So once you've put in this first statement and then you get down here, iOS is going to be like, oh, he's not making a mistake. What he's actually doing is saying, oh, instead of being assigned to area 1, I want you to reassign these to area 3. And like, oh, we're cool with that. So the area 1 network statement does not appear here. If you're doing this on the CLI and you have any interfaces that match this IP range, you're going to actually see a little message. It'll give you a little like, hey, you're changing from area 1 to area 3. And you're like, what? No, I'm not. I didn't do anything like that. That'll be a tip off. With that in mind, let's jump over to the CLI and do a little bit of bacon here. All right, so let's do a show IP interface brief, and we just want to have the interfaces that are assigned IP addresses. So you can see here we got our loopback 0 and then loopbacks 10 through 15. They have different IP addresses assigned to them. If we do a show IP proto summary, so it's show IP protocol summary, you can see that we don't have OSPF running here. So let's get in there and change that. So we're going to do router OSPF 1. I'm not going to worry about a router ID here because we really don't care. What I am going to do is show you the network and then invoking the Cisco IOS help. It says give me a network number. Let's go ahead and assign loopback 0 to a specific area. So we put in 1.1.1.1, and now the wildcard bits. And we're going to use that quote unquote host wildcard bit assignment. So I'm going to do quad zeros and I'm going to say area 0. All right, so now if I do a show run section router OSPF, it'll take just a second to think about this, and it shows that it took that. So right now your verification commands are show IP OSPF interface, and I'm just going to use int because I don't want to misspell it, screw it up. But I'll show you all the interfaces are currently running OSPF. Shows you here that this /32 address is in area 0, just like we thought it would be. Probably the better command for this is show IP interface brief. Show IP OSPF interface brief, because it gives you this output in a table form. It's a little more concise, and all we're really looking for here is the area. So we see the loopback 0 is in area 0, and here is the IP address. I'm going to go actually ahead and blow away that configuration, and the way to do that is to issue the no. So no network 1.1.1.1 quad 0 area 0. Now we can go ahead and reissue our show IP OSPF interface brief, and we don't get output. That means that it's not running on any interfaces. If we do a do show IP protocol summary, what do you think we'll see? Remember, we don't see any interfaces, so we're obviously not running OSPF, right? Well, we are, because we have the router statement. So we have OSPF quote unquote running. It's just not going to do a whole lot until we assign some interfaces. Okay, so let's do this. Let's do network. And remember, if we want to assign every single interface to a particular area, we do the quad zeros and quad 255s. And then we choose an area. I think that's what they were talking about earlier, about using area in an IP address format when it's talking about subnets. That's the only thing I could think of. Otherwise, I don't know why Cisco threw that in there. It's just a little callback to that slide earlier. Anyway, so let's go ahead and just assign this to area 0. So now if we do a do show IP interface, IP OSPF interface brief, every single interface on here that has an IP address assigned, obviously, has been assigned to area 0. Booyah, regardless of the IP address or the mask or anything. So that is our catch-all, is this quad zeros with the quad 255s. All right, so let's do a little fun here. Let's do network 1.1.0.0 and then 255.0.0 and area 1. So what I'm saying here is that I want to assign anything that is within the 1.1/16 range, which when we're looking at these interfaces is only going to be this guy. Now remember, the network mask does not have to match, it just has to fall, this IP address has to fall within this range. But you notice that I put this in the form of a network mask rather than as a wildcard mask. I should have been 0.0.255.255, and then I've assigned it to area 1. So let's do a do show run. Ah, it gave us a little clue. Remember I told you about that? It changed it from area 0 to area 1. So we know what's going to happen here. Anything in that range was formerly assigned to area 0 because everything assigned to area 0. Now it's going to be assigned to area 1. If we do show run section router OSPF, and we wait for the router to think a little bit here. Okay, you can see here that it's done a couple of things. So remember the order that we put this in. We put in this network statement first, this catch-all, and assigned everything to area 0. Now when we do a show running configuration and we're looking at the OSPF configuration, we see that that is actually listed second, even though this network statement was put in afterwards. That's iOS reordering for you. The second thing that we can see here is that the command that we issued was network 1.1.0.0 So it took that wildcard mask argument and said, you know what? I see this start with a 1. I think that you're putting in a network mask when you should be putting in a wildcard mask. Let me be nice and go ahead and convert that for you. So it converted it for you. We can show this actually one more way. If we do a network 1.1.1, 255.255.0 area 3, and then just go ahead and up arrow, and you can see here with this statement we put in a very specific network, but then our mask was really, we screwed it up again. We put in a network mask of /24 instead of wildcard bits, which would have been 0.0.0.255, and then assigned it to area 3. iOS says, oh, I know what you were up to. What you really meant to do was use a wildcard bit mask of 0.0.0.255. Ooh, thank you, iOS. You saved my bacon. And it also says, you know what? I know you gave me a network of quad 1s, but because these zeros mean must match, we really only care about the first 3 octets. So when I put this in my running configuration, I'm just going to use 1.1.1.0 because I don't care about anything in that octet. So that's an iOS conversion feature where it will convert anything that you provide for the wildcard bit argument. If it starts with a 1, it's going to assume that you accidentally put in a network mask, and it's going to convert it to a wildcard bit mask. And it's also going to truncate your network to only reflect an IP address that has the octets that we care about represented. Okay, so a quick way to get rid of all of this stuff is to issue the no router OSPF, and then your process, in this case 1. That's going to get rid of all your OSPF configurations. So now if you were to do a do show run section router OSPF, we shouldn't get any output. Exactly. So that's the quick and dirty way to get rid of your OSPF process. Only do that if you know what you're doing. Here we're in a lab, and I wanted to get rid of all those network statements without having to go in and take them out one at a time. All right, so I'm going to do a little cut and paste action here. I'm going to go router OSPF 1 to re-enable this, if I could spell it. And I'm going to paste in these network area statements. And you see this changed bit. The reason we're seeing this is because we previously had OSPF running and it keeps some of this in memory. You probably won't see this if you're just starting out fresh and you haven't configured OSPF on here. This is actually going to come in handy in just a bit here, because what I've done, I put in a catch-all. You know, this is our default. It says assign everything to area 0. Assign everything that starts with a 10 and is a /8 to area 1. Basically anything that starts with a 10, area 1. Anything that starts with 10.1, because it's more specific, assign it to area 2. And what I'm going to do here, I'm going to paste in 2 more network area statements, and let's see what happens here. Okay, well, we get changes for all these because I didn't reload this and we were running this before, but this is the one I wanted to show you. This is what we went through in the slides. You can see that 10.0.0.0/8 has changed from area 1 to area 3. We saw here earlier that it changed from area 0 to area 1. But this is that case where we put in this configuration line is exactly the same as this. So basically it's overriding the second line, because it came later, is overriding this one. So we're not going to assign anything to area 1. We're going to actually assign it to area 3. So actually what I'll do is I'll do a show history. And what it's going to show me is the configuration commands in the order that I put them in, and then I'm going to go ahead and do a do show run section router OSPF. So basically I'm going to be able to compare the order that I entered these in and what is actually in the running configuration. So this is what I typed in. Now these are all my network statements, and here's how they ended up under the OSPF process. So you can see here that they've been reordered to be more specific. And if it was the case that I had used a network mask rather than wildcard bits, it would have been converted. And that's going to actually show up in this last statement here, where I'm saying, okay, network 10.1.1.1, quad 255s. As we saw in the slides, in a world that is dictated by the logical operand OR, this would match everything. Here iOS is saying, oh wait, this wildcard mask that you gave me starts with a 1 because the first octet's 255, so it's all 1s. I'm going to go ahead and convert that. So here you can see that it changed from 10.1.1.1 with quad 255s to 10.1.1.1 quad 0s, which means that it will only match on that specific interface. And you can see here that we have 4 statements rather than 5, and we've already gone over why this guy got axed. So let's go ahead and break out of this, and I'm going to show you your verification commands, and we looked at a few of these already. So show IP OSPF interface brief, and I'll type it out for you the full way there. Actually, I'll use a tab to do that for me. That's my favorite one. It gives you a table, shows you all the interfaces, shows you the area that they're assigned to, and then their IP address along with mask. That's my favorite one. You could also do this and skip the brief. Gives you a little bit more information here, but what we're looking for today, we really only care about the interface and then the IP address and then the area assignment. All right, we just went over this on the CLI, so we'll blow through these slides. Here's your verification. You can use either the show IP OSPF interface or my favorite, the show IP OSPF interface brief. Here's the show IP OSPF interface. Gives you more information than you really need at this point, but it's a good command. And show IP OSPF interface brief. I use this far more often than show IP OSPF interface when I'm troubleshooting issues like this, because it gives you just a subsection of the information of the show IP OSPF interface, and it puts it into a table so you can quickly look at this, and you can see here's our interfaces, here's the area that they're assigned to, and here's our IP address and mask. So a lot of good information in a really concise presentation here. So you can verify your network area statements, not just the assignments of the interfaces, but the actual statements themselves with 2 different commands. Of course, you can do the show run, and we'll see that in the next slide. But you can also use the show IP protocols, and you just want to look at the OSPF section if you've got multiple protocols running, which is cool. It shows routing for networks, and that shows you this list of output here, and this is your network area commands. Basically, you just stick a network in front of those, you've basically got what you've got in the running configuration, and in the order too. They're listed in order of specificity. Ooh, word of the day. But this is pretty cool for a couple of reasons. You might be on a device that you don't have access to the show run command. In this case, you can basically get what that running configuration is for the network area commands from this command. What's more likely is the case is that you're in a Cisco lab or sitting a Cisco exam, and they say, okay, well, I'm not going to let you see what the running configuration is. Tell me what the network area statements are for this device without being able to see the show run. So you could do it from here. Like you can reverse engineer this. You just say, oh, okay. Do a show IP protocols, looked into the OSPF section. You've got all your network statements. All you have to do is pop a network at the beginning of that, and you've got actually the running configuration. And we can see this on the CLI if we do a show IP protocols, and you can hit enter here because if I do a show IP protocol summary, I'm only running OSPF. That's the only dynamic routing protocol I have. So if I put this in, it's just going to give me OSPF stuff. If you were running multiple dynamic protocols, you can actually do a grep on it where you're doing a section OSPF, and it would just give you the OSPF stuff. But anyways, the bit that we're looking for here is this routing for networks, and I will show you the other verification, which is show run, and we're just going to do a section router OSPF. This will work on routers as stands right now. This will not work on switches. What I'm talking about is the section command. So if you're on a switch and you issue show run and then grep section router OSPF, it won't work. You have to use B for begin. Anyway, that's outside the scope of this lesson. So you can see here that these statements match up verbatim, well, with the exception of the word network in front of them, with what you've got in the running configuration. And of course we can do the show run, which we just saw here. And if you want to grep just for the router OSPF output, you can do that, so you don't get clobbered with the entire running configuration, just the stuff that you're looking for. Okay, so here we go. Let's summarize this guy and get done. The OSPF network statement is used to assign interfaces to a particular OSPF area. There's two ways to accomplish this. This lesson we looked at the network area command under the routing process. There's also a separate interface level command, which is IP OSPF network. They accomplish the same thing. They go about it a little bit different. The OSPF network area command is actually going to specify an IP range. And if you have interfaces assigned an IP address within that range, it's going to assign that interface to an OSPF area that you specify. Whereas the IP OSPF network command is configured under the interface, so you'd actually have to go under each interface and enable that. Again, that's a different lesson. The only reason I even reference that other lesson is because it shows the power of the OSPF network area command, and that you can assign multiple interfaces to an OSPF area with a single command. It's going to use a network and then network mask, where the network mask is represented actually by a wildcard mask, to specify an IP address range, and then any local interfaces that match that range are going to be assigned to the area that have been specified in that command. So this is similar to an access list. If you've worked with access lists before, this will all be familiar. If not, you'll have to get familiar with wildcard masks, and we went through that in this lesson probably ad nauseum. Basically, you can think of a wildcard mask as a subnet mask with the ones and zeros flipped, where the zeros are considered must-match bits and the ones are considered don't-care bits. Speaking of wildcard masks, there are two important network area wildcard masks that you need to be aware of. Quad zeros as a wildcard mask is going to match only the IP address specified in the network portion. So it's basically the analog of an IP host route where you're matching one single interface. The quad zeros and then quad 255s. So your quad zeros is going to be your network, and then quad 255s will be your wildcard bits. That will match every single possible IPv4 interface on the device. Important thing, and we touched on this in the lesson, is that you have to use quad zeros as your network address. So if you have an interface whose IP address matches multiple network area statements, it's going to use the one with the more specific match. Again, if you've worked with access lists, you're familiar with this concept. What's actually going to happen in modern iOS versions is it's going to take your network area statements, and it's going to, regardless of what order you imported them, it's going to take them in the running configuration and order them from most specific to least specific. So when iOS is doing a comparison of an interface IP address, it's going to match the most specific one. Older versions of iOS, and I'm throwing this in here basically for historical purposes now, if you're running something, I think it's 12.2 and before, hopefully you never run across it in production, but if you do, you have to keep in mind that older versions actually keep the order that you've inputted these, so it's going to be really important that you put your most specific network area statements first and then put them in descending order of specificity. Modern iOS versions will do this for you, so it's not going to be a big problem. The other thing that you have to keep in mind is that if you enter a wildcard mask that starts with a 1, so basically if your first octet is anything other than 0, iOS is going to look at that and say, oh, you know what? This guy accidentally put in a network mask rather than a wildcard mask, and it's going to go ahead and inverts the 1s and 0s so that your network mask turns into a wildcard mask. This is actually a neat feature. It's helpful in a lot of cases, but if you're not expecting it, might end up with a couple of cases where your iOS is doing something that you didn't think it was going to be doing based on the command that you've inputted. So what I would suggest doing is exactly what I had set up in our little lab portion here. Is I would get a router, regardless if it's a physical router or a Dynamips first instance of a router. You only need one. Create a bunch of loopback interfaces, assign different IP addresses and different network masks to those loopback interfaces, and then go ahead and enable an OSPF process with your router OSPF and then whatever process number you want to do, and then start playing with network area commands. Definitely use the catch-all, the quad 0, quad 255 command to assign every single interface to a specific area. Also use the quote-unquote host one where you're specifying specific IP address, and then the quad 0 says the wildcard bit to assign specific interfaces. Just play around with it. Create a bunch of loopbacks, assign them to different areas, get used to working with this command. You'll be able to see the ins and outs of it and get used to wildcard masks at the same time. Anywho, thanks once again for joining me in the Packet Lab. As always, I hope this helps you on your route to becoming a